Midday in the Australian interior is usually a time of restraint. Heat presses down, cicadas grind the air into a static hum, and most large animals minimize movement to conserve water and avoid exposure. Yet here, under a hard white sun, kangaroos are grazing openly across a shallow grassland basin. They stand with their heads down longer than expected, muzzles sweeping left and right, forearms tucked, tails grounded like counterweights. Ears pivot lazily but not with urgency. The tree line that once dictated their spacing and timing sits ignored in the background. There is no tight clustering, no rapid head-up scanning, no sudden freezing at distant movement. What looks like calm is not confidence. It is the absence of a pressure that once structured every decision they made. Fear, in intact ecosystems, is not a panic response. It is a map. For kangaroos, that map is drawn by predators they rarely see but constantly account for. Ambush hunters that use cover, angles, and patience rather than pursuit. The map tells them where to feed briefly and where to linger, which paths to cross quickly and which areas to avoid altogether. It distributes grazing pressure across the landscape, prevents plants from being hammered in one place, and maintains a mosaic of cover heights that benefits everything from insects to ground-nesting birds. Fear does not mean constant stress, it means constant calibration. Muscles tense and release, ears scan, eyes adjust for movement, and internal clocks align, feeding with moments of lower risk. This invisible architecture shapes landscapes as reliably as rainfall. What happens when that architecture weakens is subtle at first. Kangaroos do not suddenly explode in number or turn reckless overnight. Instead, the first shift is temporal. They extend feeding bouts in places they once treated as temporary. A grassy flat near a tree line, once used in quick pulses, becomes a reliable lunch spot. The energy math seems favorable: less movement, more intake, fewer interruptions. Thermoregulation still matters. Kangaroos dissipate heat through panting and licking their forearms to promote evaporative cooling. But risk no longer constrains timing. Midday grazing increases, not because it is optimal, but because nothing is telling them not to. Over time, this changes the ground itself. Plants that evolved under episodic grazing pressure are cropped too low, too often. Root reserves are depleted, regrowth slows, bare patches widen, exposing soil to heat and wind. The loss of grass height removes visual obstruction that once hid joeys when females paused to feed. Kangaroos carry their young in a pouch for months, but the transition period, when joeys begin to emerge, test mobility, and retreat frequently, is one of extreme vulnerability. Cover matters then, not just from predators, but from temperature extremes. Open ground radiates heat during the day and sheds it rapidly at night. The microclimate becomes harsher precisely where feeding pressure is now highest. This is where the delayed bill comes due. Adult kangaroos appear healthy for years. Body condition remains strong, reproduction continues, and from a distance the population seems stable or even thriving. But juvenile survival quietly declines. Heat stress increases during exposed foraging. Mothers spend longer feeding and less time repositioning to shaded zones. Joeys, still learning spatial awareness, are more likely to be left temporarily exposed. Small losses compound across seasons, unnoticed until recruitment weakens. The system does not crash, it thins. What looks like peace is actually a slow erosion of resilience. The change is not confined to kangaroos. Overgrazed patches reduce seed production for grasses and forbs that rely on staggered consumption to regenerate. Invertebrate communities shift as soil moisture drops and plant diversity narrows. Birds that once nested in dense ground cover abandon the area. Even fire behavior is altered. Short, sparse grasses carry flames differently than mixed-height vegetation, changing burn intensity and spread. These feedbacks loop back to the kangaroos themselves, tightening the bottleneck on habitat quality without any single dramatic event to mark the transition. Humans encounter the consequences at the margins first. As feeding zones expand into previously avoided open corridors, kangaroos cross roads more frequently and at less predictable times. Their movement patterns flatten, no longer pulsed around perceived danger. Vehicles meet bodies built for explosive acceleration, not evasive maneuvering at close range. Collisions rise. On farmland, extended grazing pressure pushes kangaroos into crops for longer periods, intensifying conflict with landowners. The animals are blamed for numbers, when the deeper issue is behavior shaped by a missing signal. It is tempting to interpret this as a simple overpopulation problem or to frame predator absence as a moral victory. Fewer kills, fewer carcasses, fewer visible moments of violence. But ecosystems do not measure health by the absence of death. They measure it by distribution, timing, and flow. Predators do more than remove individuals. They sculpt decisions. Without that sculpting force, prey animals default to short-term efficiency. Energy gained now outweighs risks no longer perceived, even if those risks once prevented long-term damage. Kangaroos are superbly adapted to reading landscapes. Their large ears can rotate independently, triangulating sound. Their eyes, positioned laterally, offer wide fields of view sensitive to motion. Their powerful hind limbs allow rapid escape when danger is detected. These traits evolved not to eliminate fear, but to manage it. When fear disappears, the adaptations do not vanish. They simply idle. The animal becomes less responsive, not because it is safer, but because the information stream it evolved to process has thinned. There is an irony here that only becomes visible with time. Landscapes without predators often feel quieter to humans. Fewer sudden movements, fewer carcasses, more animals visible in the open. This visual calm is mistaken for balance. Yet beneath it, decision-making degrades. Animals overuse space, simplify behavior, and unknowingly undermine the conditions their offspring will need. The cost is deferred, paid not by the adults thriving now, but by the young that will struggle later. In intact systems, fear creates restraint without stagnation. Kangaroos move, feed, retreat, and return in rhythms that align with plant recovery and seasonal stress. The land breathes with them. Remove the fear map, and movement becomes blunt. Patterns blur. The land stops breathing and begins to erode quietly. What looks like freedom is actually the loss of information. And without information, even the most efficient animal makes poor decisions at scale. Standing at the edge of that midday grassland, it is easy to miss all of this. The scene appears pastoral. Animals at ease, light shimmering off fur, no visible threat. But ecology is not judged by snapshots. It is judged by trajectories. And the trajectory that begins with fearless grazing does not end in harmony. It ends in thinner cover, hotter ground, fewer young, and a landscape that has forgotten how to say no. Dawn breaks unevenly across the Australian interior, light spilling first into the low swales before climbing the ridgelines. A pair of dingoes moves through this half-lit space, with an ease that feels almost casual. They do not fan out. They do not test the wind. They do not pause to listen for the telltale shuffle of prey repositioning ahead of them. Instead, they angle directly toward a grazing mob already visible in the open. The hunt, if it can still be called that, is short. A brief burst of movement, a stumble, a clean kill, no prolonged chase, no explosive scatter of fleeing bodies. For the dingoes, the first consequence of prey losing fear is abundance made simple. In predator-prey systems shaped over deep time, ease is rare. Predators expect resistance, prey that bolts early, splits unpredictably, or vanishes into cover before contact is made. That resistance forces predators to burn energy, to fail often, and to make choices about when a hunt is worth the cost. Dingoes evolved inside that calculus. Their long legs and endurance favor pursuit, their jaws designed to subdue rather than crush, their intelligence tuned to reading hesitation and weakness in moving targets. When prey no longer reacts appropriately, when vigilance dulls and escape timing falters, the predator does not simply kill more indiscriminately. It adapts. The first adaptation is selectivity. When effort drops, choice increases. Dingoes begin to favor certain individuals. Animals in poorer condition, juveniles that hesitate, adults encumbered by injury or heat stress. Kills become cleaner, faster, and more predictable. Less energy is spent per meal, which means more time is available for movement, territorial patrol, and social behavior. The predators are not becoming more violent, they are becoming more efficient. In ecological terms, this matters far more. Efficiency reshapes feedback loops. As dingoes remove prey with minimal disruption, the broader prey population initially benefits from reduced panic. Grazing becomes steadier, reproduction continues, and numbers rise. This looks, superficially, like prey thriving alongside predators. But the growth is uneven. Habitat degradation accelerates as fear-driven avoidance disappears. Overgrazed areas expand, cover thins, and animals cluster in increasingly exposed, resource-poor zones. Disease transmission increases as individuals spend longer feeding in close proximity, noses down, bodies brushing, parasites moving easily through stressed populations. The crash, when it comes, is not triggered by predators alone. It is triggered by habitat failure and physiological strain. Dingoes, now accustomed to abundant and easy prey, encounter a sudden decline not in numbers, but in quality. Animals are thinner, more parasite-laden, less resilient. Mortality spikes, not just from predation, but from starvation, heat stress, and infection. The predator becomes the visible agent of death, but the underlying cause is the earlier loss of behavioral structure that once regulated space use. Within dingo packs, the effects ripple outward. When hunting is difficult, packs are tightly organized, roles are clear. Breeding is limited, with dominant pairs suppressing reproduction in subordinates. Pup survival is constrained by food availability and the need for coordinated provisioning. When food becomes easy, those constraints loosen. More pups survive. Subordinate breeding increases. Packs grow larger and territories expand to encompass newly productive zones. This is not aggression spiraling out of control. It is opportunity expressed through social flexibility. Expanded territories bring new interactions. Dingoes range farther, crossing landscapes that once required careful timing and cooperation. They encounter other packs more frequently, increasing both conflict and gene flow. Vocalizations carry farther across open ground stripped of dense vegetation, changing how territories are advertised and defended. The predator population, like the prey population before it, enters a phase of expansion driven by short-term abundance. Here, the common narrative falters. Dingoes are often cast as destabilizers, blamed for prey declines or livestock losses without context. Yet in this sequence, they are responding logically to altered conditions. They did not remove fear from the system. They reacted to its absence. Their increased efficiency exposes weaknesses already present. They become catalysts, accelerating processes that would otherwise unfold more slowly and invisibly. There is a biological elegance to this role. Predators often reveal ecosystem health by amplifying imbalances. When prey behavior is intact, predators regulate without dominating. When prey behavior collapses, predators magnify the consequences, making dysfunction harder to ignore. In this sense, dingoes function less as villains and more as diagnostic instruments. They translate behavioral decay into measurable outcomes: population swings, disease outbreaks, and habitat shifts. The human response often misreads this signal. Rising predator numbers or expanded territories are interpreted as overreach. Control measures are implemented: culling, exclusion fencing, lethal deterrence, aimed at reducing the visible agent rather than addressing the invisible cause. This can temporarily suppress predation pressure, but it further destabilizes social structures within dingo populations. Disrupted packs fragment. Younger and less experienced hunters target easier prey, including livestock, and the feedback loop tightens. Meanwhile, prey populations, already compromised by habitat degradation, lose even the selective pressure that once removed weak or diseased individuals. Mortality shifts from predation to starvation and sickness, outcomes that are less visible but no less lethal. The landscape accumulates bodies not at kill sites, but at waterholes, along fences, and beneath sparse shade where animals fail to cope with environmental extremes. The system appears quieter, but it is not healthier. Dingoes themselves are shaped by this instability. Larger packs demand more coordination, more negotiation, more internal restraint. When food abundance fluctuates sharply, social tension increases. Aggression within packs rises. Dispersal rates change as young animals are forced to leave overcrowded territories, pushing into human-dominated landscapes. Again, the predator is blamed for crossing boundaries it once respected, even though those boundaries were defined by prey behavior and habitat structure that no longer exist. The twist lies in recognizing causality. Dingoes are not the architects of collapse. They are accelerants. They respond to ease with efficiency, to abundance with expansion, to instability with movement. Each response is adaptive in isolation, Together, they reveal a system that has lost its internal checks. Removing or vilifying the predator does not restore those checks. It erases the messenger. In intact ecosystems, predators impose a kind of discipline that benefits the whole. They force prey to make better decisions, to distribute pressure, to maintain cover, to respect thermal limits. In doing so, predators also limit themselves. Hunting remains costly enough to prevent runaway growth. Packs stay lean, territories balanced, reproduction restrained. Fear, flowing upward from prey to predator, regulates both sides. When fear disappears at the base, that regulation dissolves. Dingoes step into the vacuum not as tyrants, but as opportunists shaped by evolutionary logic. They become the visible edge of a much deeper problem. A landscape where decisions are no longer constrained by consequence until it is too late. In that light, the predator is not the enemy of balance. It is the proof that balance has already been lost. The riverbank should never look like this. At first glance, it appears abundant, lush grasses pressed flat into feeding mats, water lapping gently against a crowded shoreline, dozens of broad-backed bodies shoulder to shoulder where forest should begin. Capybaras cluster along the edge, as if the river itself has become a feeding trough. They wade knee-deep, mouths working continuously, eyes half-lidded, barely lifting their heads between bites. There is no tension in their posture, no rapid scanning of the water's surface, no sharp retreat when ripples move against the current. The edge is packed because nothing is telling them to leave. In intact Amazonian systems, riverbanks are not places to linger. They are transition zones, rich but dangerous, productive but exposed. Capybaras evolved to exploit these edges carefully. They graze in bursts, enter the water quickly when threatened, and retreat into cover when pressure rises. Fear governs river time. It dictates how long a group feeds before dispersing, how tightly they cluster, and how often they rotate individuals away from the most exposed positions. This behavior is not incidental, it is structural. It limits damage to the bank, preserves vegetation, and maintains a fragile boundary between land and water that countless other species depend on. Remove fear from that equation, and the math collapses. Capybaras do not become reckless. They become efficient. They stay longer because the cost of staying appears low. Grass is abundant. Escape routes are clear, and nothing interrupts the feeding rhythm. Over days and weeks, short visits turn into occupation. Hooves churn the saturated soil. Vegetation is eaten faster than it can regenerate. Root systems that once bound the bank together are stripped away, leaving exposed sediment vulnerable to every passing swell and rain pulse. Erosion follows not as a dramatic collapse, but as a slow bleed. Fine particles slide into the water column, turning clear shallows opaque. The river grows heavier, clouded with suspended silt that alters light penetration and oxygen exchange. Fish nurseries, those quiet, shallow margins where fry shelter among submerged grasses, begin to fail. Eggs smother, juveniles lose visual cover. Predation pressure on young fish rises even as adult fish struggle with degraded feeding grounds. The impact radiates outward, invisible from the surface but profound in consequence. As fish communities shift, insects respond. Aquatic larvae that rely on specific substrates disappear, replaced by species tolerant of murkier, warmer water. Mosquitoes exploit stagnant pockets created by uneven erosion. Biting flies increase along denuded banks where shade is gone and humidity remains high. These are not exotic invaders, they are opportunists filling niches opened by physical disturbance. The river edge, once a finely tuned interface, becomes a blunt instrument reshaping the food web. Capybaras are not predators, but their effect rivals one. Their sheer biomass and social feeding behavior turn them into ecosystem bulldozers without intent or malice. Each individual consumes modestly. The damage comes from scale and timing. Large groups feeding continuously in the same place overwhelm the land's capacity to recover. What once required dozens of visits over a season now happens in a single week. The system loses its ability to buffer impact. Disease risk climbs alongside physical degradation. Capybaras are excellent hosts for parasites, particularly ticks that thrive in disturbed, grassy margins close to water. When groups linger, parasite loads build, ticks drop off into the environment, climb vegetation, and wait. with capybaras spending more time near human-modified edges, fields, paths, village clearings. The overlap intensifies. Humans notice the animals first. They appear tame, numerous, almost pastoral. The parasites arrive later, quietly, carried on clothing, livestock, dogs. This is where perception becomes dangerous. Capybaras are widely viewed as benign, even charming. Their calm demeanor and social tolerance make them seem harmless, an emblem of peaceful coexistence. But ecological impact does not correlate with temperament. The same traits that make capybaras appealing, large size, group living, dietary flexibility, also make them powerful agents of change when behavioral constraints disappear. Villages and farms feel the pressure, not through dramatic conflict but through accumulation. Crops near waterways suffer heavier grazing. Riverbanks used for washing or fishing become unstable and muddy. Tick encounters increase. Livestock pick up parasites that reduce weight gain and fertility. None of this points directly back to fear loss. Instead, blame disperses. Too many animals, too little control, bad luck. The underlying mechanism remains hidden because it operates through absence rather than presence. Capybaras themselves are not thriving in a meaningful sense. High-density feeding increases stress and disease transmission within groups. Calves, which rely on concealment and rapid movement between land and water, are more exposed on flattened banks. The same erosion that harms fish nurseries also removes shallow refuges that capybaras use to thermoregulate and evade threats. What begins as apparent abundance carries the seeds of later vulnerability. The Amazon has always been shaped by pressure gradients. Predators, floods, seasonal scarcity, all impose limits that distribute life across space and time. Capybaras evolved within those limits. Their grazing patterns once complemented flood pulses, trimming vegetation without destabilizing soil, fertilizing banks without stripping them. Fear was the invisible regulator that kept that balance intact. When fear fades, behavior simplifies. Complexity gives way to repetition. Animals return to the same safe-feeling spots again and again, unaware that safety itself is eroding beneath them. The riverbank becomes wider, barer, louder with insects, poorer in fish. The change is not sudden enough to alarm, but relentless enough to transform. This is the true twist. The capybara does not need to change its nature to become destructive. It only needs permission to linger. Remove the cues that once enforced movement and restraint, and a grazer becomes an engineer of collapse. Not through violence, not through excess appetite, but through persistence. The Amazon does not break from a single blow. It unravels when the quiet rules that govern time, fear, and movement are ignored. The forest does not announce when it breaks its own rules. It simply goes quiet in the wrong way. A jaguar moves through this silence at first with effortless success. The trails are crowded, hoof prints overlap. Game paths converge unnaturally toward water and open clearings where prey now linger too long. The cat does not need to stalk for hours or calculate wind and cover with the precision that usually defines its hunts. It steps into abundance. A single ambush yields a heavy-bodied meal. Another follows days later, then another, all within a narrow stretch of riverbank and floodplain forest. For a predator built to exploit brief windows of opportunity, this feels like a gift. Jaguar hunting strategy evolved around scarcity and dispersion. Prey animals, capybaras, deer, peccaries, normally space themselves across large territories, driven by fear as much as by food. That spacing forces jaguars to patrol widely, to learn the geography of resistance. Their muscular bodies, oversized skulls, and bone-crushing bite are not tools of brute force alone. They are solutions to a problem of access. When prey is alert and scattered, a jaguar must kill decisively, often in water or dense cover, before the opportunity vanishes. Energy expenditure is high, success uncertain, and territory size reflects that reality. When fear collapses at the base of the system, that spatial discipline disappears. Prey clumps. They gather along river edges, mineral licks, and open feeding zones that now feel safe. The jaguar benefits immediately. Hunting becomes local. Travel distances shrink. Kills cluster around predictable hotspots. The cat eats well, expending less energy per calorie gained. On the surface, this looks like predator success, even dominance. But the same behavioral simplification that helped the jaguar now begins to undermine it. Fear matters to predators not because they experience it in the same way as prey, but because it structures prey behavior in ways that stabilize food availability. Fear keeps prey moving. It prevents overuse of a single patch. It ensures that after a kill, the remaining animals disperse, forcing the predator to follow and preventing localized depletion. Without that dispersal, the jaguar unknowingly overdrafts its own hunting grounds. As prey density spikes in small areas, vegetation collapses faster than it can recover. Riverbanks erode, understory thins, water quality degrades. The prey population remains numerically high for a time, but its nutritional quality drops. Animals grow thinner, parasite loads increase, juveniles fail more often. What was once a renewable resource becomes a fragile stockpile concentrated in shrinking pockets of habitat. For the jaguar, the consequences unfold slowly and brutally. Prey hotspots attract not just one predator, but several. Territories that once overlapped minimally now collide. Jaguars are solitary by necessity, not preference. Their hunting strategy depends on space. When space compresses, conflict rises. Scent marks overlap. Trails are reused. Encounters become unavoidable. Jaguar fights are not ritualized displays. They are violent, risky, and often injurious. A fractured canine, a torn shoulder, an infected bite wound, any of these can end a hunting career. In intact systems, such encounters are rare because prey distribution keeps predators apart. Here, abundance pulls them together. The very ease of hunting creates competition intense enough to destabilize the population. Risk-taking escalates. Jaguars begin hunting closer to human settlements, not because they prefer livestock, but because prey now congregates near disturbed edges where fear is already low. These are the same zones where capybaras linger, where peccaries raid crops, where deer cross paths and fences. Jaguars follow the food. Encounters with humans increase. Defensive killings rise. The predator's reputation darkens, even though its behavior is a logical response to altered prey dynamics. Physiologically, the jaguar is ill-equipped for sustained instability. Its body is optimized for short, explosive effort followed by rest. Injuries heal slowly. Chronic stress, caused by frequent encounters, disrupted territories, and unpredictable food quality, suppresses immune function. Parasites that once posed little threat gain traction. A predator at the top of the food web has nowhere to offload stress. It accumulates. There is a cruel irony in this phase. The jaguar appears everywhere. Camera traps capture it more often. Tracks are found near villages. Stories circulate of increased sightings. To many observers, this signals a predator problem. Calls for control grow louder. Yet beneath the visibility is a thinning core. Fewer individuals reach old age. Reproductive success falters as females struggle to raise cubs in crowded, contested landscapes. Cubs born into these hotspots face higher mortality, not from starvation, but from conflict and disturbance. Territory, the invisible currency of survival, loses value when prey no longer enforces boundaries. Jaguars concentrate around the same few productive zones, abandoning the broader mosaic of forest and floodplain that once supported them. When a hotspot collapses, through overgrazing, erosion, disease, or human intervention, the predators do not smoothly redistribute. They scramble, some starve, some push into marginal habitat, some are killed. This is what ecological overdraft looks like. Energy is withdrawn faster than the system can replenish it. Short-term gains mask long-term deficits. The jaguar, often portrayed as the ultimate winner in predator hierarchies, becomes trapped in a boom-and-bust cycle, driven not by its own excess, but by the absence of restraint elsewhere. Fear is often misunderstood as a negative force, something to be eliminated for the sake of harmony. But in ecosystems, fear is information. It tells prey when to move, when to stop, when to leave something unfinished so it can regrow. That information flows upward. Predators rely on it indirectly to maintain spacing, reduce conflict, and keep food landscapes resilient. Remove fear, and the entire network loses resolution. The jaguar's legendary bite, capable of piercing turtle shells and crushing skulls, did not evolve for domination. It evolved for efficiency in rare moments of access. When access becomes constant, efficiency turns destructive. The predator is no longer selecting against weakness. It is harvesting density, and density, once removed, does not return easily. In the end, removing fear does not create a world where predators finally win. It creates a world where predators burn through capital they did not know they were borrowing. The jaguar walks into the easiest hunting of its life, and for a brief moment, it seems like the forest has tipped in its favor. Then the ground erodes, prey thins, rivals close in, and the system flips. The apex predator is left navigating a landscape stripped of the very structure that once made its power sustainable. The Amazon does not collapse loudly, it hollows out. And when fear is erased, even the strongest animal in the forest finds itself standing on borrowed ground, paying interest in blood, injury, and loss long after the feast has ended. The change does not announce itself with silence, it arrives as efficiency. Seals leave the haul-out and cut straight lines through blue water instead of tracing broken, cautious arcs along kelp edges. They surface less often to scan. They dive without hesitation, linger longer between breaths, and cross open channels at midday that once demanded detours at dawn or dusk. To an untrained eye, this looks like confidence. To the ocean, it is the first crack in a system held together by fear. In healthy coastal ecosystems, fear is not panic, it is geometry. It bends movement. It forces prey to choose inefficient routes, to feed in bursts, to abandon rich patches before they are fully exploited. Great white sharks are the architects of that geometry. They do not need to kill often to shape behavior. Their value lies in uncertainty. A white shark may patrol a seal colony for weeks, unseen, detected only through subtle cues, abrupt silence in baitfish schools, the tightening of seal groups near cover, the sudden abandonment of exposed feeding lanes. These cues ripple outward, changing where energy moves through the system. When that pressure weakens, the geometry straightens. Seals optimize. They take the shortest path between rest and food, the deepest dives in the most productive zones, the longest feeding windows in open water. Their metabolic math improves. Less zigzagging means less energy burned per calorie gained. Pup survival initially rises. Populations grow. To observers tracking numbers alone, this appears as success, but behavior always precedes consequence. By abandoning the edges and gradients that once defined safe feeding zones, seals redistribute predation pressure across the seascape. Fish schools that once clustered near complex habitats, reefs, kelp forests, broken bottom, now face sustained, concentrated feeding in open water. Some species retreat deeper or toward new refuges. Others cannot. The map of pressure redraws itself. Reefs feel this first. Herbivorous fish that once grazed evenly across coral and algal beds now avoid certain areas while overusing others. Algae blooms in the gaps. Coral recruitment falters where grazing becomes inconsistent. Invertebrate communities shift as sediment settles differently without the stabilizing presence of structured reef life. Predatory fish respond to the new distribution, concentrating where prey remains dense, abandoning marginal zones entirely. The system grows louder with activity in some places and eerily quiet in others. This unevenness is instability in disguise. Diversity thrives on gradients, on transitions between risk and refuge, abundance and scarcity. When fear collapses, gradients flatten. The ocean does not empty, it clumps. Energy funnels into fewer pathways. Those pathways overload. Great white sharks are not blind to this shift. They are exquisitely tuned to movement and density. Their sensory systems, lateral lines sensitive to pressure waves, electroreception capable of detecting muscle contractions, evolved to exploit brief moments of vulnerability in otherwise wary prey. When seals linger, sharks find easier opportunities. Attacks become more predictable in space and time. Success rates rise. From a purely energetic perspective, this is a windfall. But predators, like prey, depend on distribution. White sharks are built for vast ranges, not localized abundance. Their physiology reflects this. They regulate body temperature through regional endothermy, maintaining elevated muscle and organ temperatures that allow bursts of speed and endurance in cold water. This adaptation demands energy. It assumes movement across large territories where prey is spread thin but reliably replenished. As seals cluster and feeding hotspots stabilize, sharks converge. Multiple individuals patrol the same corridors, the same drop-offs, the same seal transit routes. Encounters increase. Competitive pressure rises. Risky behavior follows: closer approaches to shore, shallower strikes, daylight attacks in unfamiliar contexts. Injuries that once would have been rare accumulate: damaged fins from collisions, jaw trauma from hurried bites, infections from wounds sustained in crowded hunting grounds. The system begins to cannibalize its own advantages. Local prey depletion follows concentrated predation, forcing sharks to linger longer or push into marginal zones where hunting is less efficient and more dangerous. Some individuals leave entirely, searching for new grounds. Others remain, drawn by memory and residual success, even as returns diminish. The ocean, once structured by movement, becomes a series of overdrafted accounts. Humans enter this story at the most misleading moment. Beaches feel alive, fish are visible, seals pass close to shore. The absence of obvious shark presence is interpreted as safety rather than as a shift in behavior. Swimmers venture farther, surfers linger longer in open water, kayakers cross channels once avoided. Risk perception lags behind ecological change. When encounters occur, they are framed as anomalies, sudden intrusions of danger into an otherwise benign environment. But from the shark's perspective, the environment has already changed. Prey density near shore is higher. Feeding lanes overlap with human recreation zones. The shark is not invading a safe ocean. It is following redistributed energy. The tragedy is that by the time instability becomes visible, it is already entrenched. Fish populations fluctuate wildly. Some species explode in number, freed temporarily from predation pressure, only to crash when habitat quality collapses or disease spreads through dense schools. Others vanish quietly, unable to adapt to the new pressure map. Reefs lose resilience. Kelp forests thin. The ocean grows noisier with certain forms of life, while losing its capacity to buffer change. White sharks, often blamed as the architects of fear, are in fact its conduits. Their presence transmits information through the food web. Remove or diminish that signal, and the ocean does not relax into harmony. It loses resolution. Decisions become locally optimal and globally destructive. There is a subtle lesson here about stability. Calm surfaces do not guarantee balance. An ocean without visible fear can be an ocean burning through its structural capital. The noise of life, schools flashing, seals feeding boldly, humans crowding the water, masks a deeper erosion. The checks that once prevented overuse are gone. The system runs hot. In time, the sharks pay the price as well. Reduced prey quality, increased competition, and heightened human conflict thin their numbers. Migration routes fragment. Genetic exchange slows. A predator built to roam finds itself constrained by the consequences of abundance mismanaged. The twist is not that fear makes the ocean quiet. Fear makes it sustainable. It creates pauses, detours, inefficiencies that allow recovery. When fear fades, life rushes in to fill the space, louder and denser than before. For a moment the ocean feels full, then the structure collapses beneath the noise. Great white sharks do not rule the sea through terror. They stabilize it through influence. When that influence weakens, the ocean does not become safer, it becomes brittle. And brittle systems do not break immediately. They shatter when pressure finally arrives, leaving behind an ocean that was once loud with life and is now struggling to remember how to hold itself together. The mistake lasts less than a second. A small predator, lizard, bird, or snake, lunges at a flash of color on the forest floor and closes its jaws around something that should not be eaten. There is no dramatic recoil, no instant rejection. The predator hesitates just long enough for chemistry to cross a biological boundary. Alkaloids seep across mucous membranes. Sodium channels misfire. Muscles stutter. The predator releases the frog, but the delay is costly. In some cases, it will recover after hours of disorientation. In others, it will not recover at all. The lesson, if it is learned, is written into nerve tissue. This moment is where fear begins, not as instinct, but as memory. In the Amazon understory, poison dart frogs are not fast, large, or aggressive. Their power does not lie in escape or confrontation. It lies in information. Bright colors, electric blues, toxic yellows, blood reds, are not camouflage. They are signals broadcast openly in a crowded visual environment. These frogs do not hide from attention. They weaponize it. But the signal only works if predators are afraid to interpret it. Fear here does not originate in the frog. It originates in the predator's nervous system, shaped by experience. Aposematism, The use of warning coloration is not an inherent shield. It is a contract between species. The frog advertises danger. The predator must believe it. If belief erodes, the system unravels. In intact ecosystems, predator learning is conservative. A single bad encounter is enough. Sampling is rare because the cost is high and remembered. Young predators observe adults avoiding certain colors, shapes, or movements. Cultural transmission reinforces individual experience. Over time, bright frogs become ecological negative space, seen but not touched, present but excluded from the menu. This allows dart frogs to occupy diurnal niches on the forest floor, calling openly, foraging slowly, investing energy in reproduction rather than evasion. Fear, in this context, flows upward. It shapes predator behavior as much as prey survival. When that flow weakens, the change is subtle but destabilizing. Predators begin to sample more often, not because they are ignorant, but because the cost-benefit calculation shifts. If predator communities are disrupted through population turnover, habitat fragmentation, or altered prey availability, young, inexperienced hunters become more common. Without strong reinforcement from elders or consistent exposure to consequences, warning colors lose clarity. Brightness becomes curiosity instead of prohibition. Sampling bites increase. Most are tentative, quick mouthings followed by release. But chemistry does not require commitment. Each contact delivers a dose. Some predators die outright. Others survive but suffer neurological damage, impaired coordination, or altered sensory processing. A few, through sheer variability, tolerate low doses and learn that the risk is survivable. This is where evolution gets strange. Predators that partially tolerate toxins do not become immune in a clean, linear way. Instead, they adapt around the poison. Feeding behavior shifts. Frogs are mouthed and discarded more frequently, increasing injury and stress for the prey even when death does not occur. Predators may target smaller individuals, consume limbs, or exploit moments of vulnerability during breeding or metamorphosis. The warning signal no longer guarantees safety. It merely complicates the interaction. For the frogs, this is catastrophic. Their entire strategy assumes recognition. Bright colors make hiding worse, not better. Movement patterns evolved around visibility, not concealment. When predators no longer reliably avoid them, dart frogs face a dilemma they are poorly equipped to solve. Some populations respond by retreating. Individuals spend more time under leaf litter, in bromeliads, or in shaded crevices where visibility drops. Activity shifts toward dawn, dusk, or night, times when visual signals are less effective. Calling behavior changes, quieter, shorter, less frequent, reducing mating success. These are not refinements, they are emergency measures. Others do not adapt fast enough. Local extinctions follow, often without obvious cause. The frogs were toxic. The habitat remained intact, yet the signal failed. The ecological consequences ripple outward. Poison dart frogs are not just icons of toxicity. They are integral components of Amazonian micro-ecosystems. They control insect populations, particularly ants and mites, whose own chemical defenses contribute to the frog's toxicity through diet. They transport nutrients between canopy pools and forest floor. Their tadpoles shape microbial communities in phytotelmata, tiny water bodies held in plants that host entire food webs. When frog populations decline or alter behavior, these systems destabilize. Insect numbers spike or shift composition. Ant communities reorganize, affecting seed dispersal and soil turnover. Microhabitats lose their keystone occupants, collapsing quietly. The forest does not notice immediately. It notices later, when small processes no longer cancel each other out. Fear's role becomes visible only in its absence. There is a deeper principle at work here. Aposematism is not just about toxicity. It is about trust. The prey trusts that the predator will remember. The predator trusts that the signal is honest. That mutual recognition stabilizes interactions without constant enforcement. It reduces unnecessary death on both sides. Predators avoid costly mistakes. Prey avoid constant flight. Energy is conserved. Space is shared through rules rather than force. When fear erodes, enforcement returns. But it is inefficient and brutal. More predators die from poison exposure. More frogs are injured or killed during sampling. Selection pressures intensify, favoring extreme traits, higher toxicity, more exaggerated coloration, or, paradoxically, complete abandonment of visibility in favor of cryptic strategies. The middle ground disappears. This instability does not remain localized. Migration patterns shift as predators range wider to compensate for unreliable prey. Spacing rules collapse as animals concentrate in perceived safe zones. Competition increases. The forest grows louder with movement and conflict, then quieter as populations thin. The final irony is that poison dart frogs themselves do not produce their toxins in isolation. Their alkaloids are derived from dietary sources, specific ants, beetles, and mites. Habitat changes that affect insect availability directly affect frog toxicity. As ecosystems destabilize, frogs may become less poisonous, even as predators sample them more frequently. The signal weakens at both ends simultaneously. At that point, color becomes liability without protection. What emerges from this cascade is a unifying truth. Fear is not a byproduct of danger. It is a structural force. It binds systems together across levels: behavioral, physiological, evolutionary. It allows bright colors to mean something, migrations to follow invisible corridors, territories to exist without constant violence. It is the glue behind spacing, timing, and restraint. Remove fear, and rules dissolve. Animals do not become freer, they become louder, riskier, more experimental. Life accelerates into unstable configurations. Some species exploit the chaos briefly, most pay for it later. The poison dart frog, small and fragile, exposes this truth more clearly than any apex predator ever could. Its survival depends entirely on fear existing in someone else's mind. When that fear holds, the frog can afford to be slow, bright, and open. When it fails, even poison is not enough. The Amazon is not held together by strength alone. It is held together by remembered mistakes, learned boundaries, and signals that mean the same thing to many species at once. Fear is the medium through which that meaning travels. Strip it away, and even the most vivid warnings fade into noise, until the system no longer remembers how to stop touching what will kill it.